Good morning. Myself, Dr. R Kesavulu, Associate Professor, Department of Physics, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Today, I am going to discuss about the main topic is laser glass spectroscopy. In that topic, we are going to discuss about today white light emission in dysprosium 3+ doped lead fluorophosphate glass. So, last and previous session, we discussed different kind of transition metal ions. That means last previous 5 lectures we have discussed on the transition metal ions of spectral studies and EPR analysis of the transition metal ions only. So these are the mainly iron 3+, Mn2+, chromium 3+, manganese 2+ ions we are discussing last 5 lectures. Now we are going to discuss about the rare earth ions, that means lanthanide doped ions, that is F black elements. We are going to discuss about the today topic. So today topic is the white light emission in dysprosium 3+ doped lead fluorophosphate glasses. Today outline of the today talk is on the introduction on the dysprosium doped lead fluorophosphate glasses and experimental methods and techniques of the dysprosium 3+ ions doped lead fluorophosphate glasses and resultant discussion of the dysprosium 3+ doped lead fluorophosphate glasses. Finally, summary or conclusion of the white light emission in dysprosium 3+ doped lead fluorophosphate glasses. So these are the we are going to discuss about today talk. So first we have to summarize the introduction. First, lanthanide ions have been playing an important role in modern lighting and display fields due to abundant emission color on their 4F to 4F transition and also 5D to 4F transition. These are the mainly belongs to the lanthanide ions. That means rare earth ions are lanthanide ions in the lanthanide ion group. If you see the periodic table, you have see the lanthanide ions and actinides. So lanthanide ions are the F black elements. So that is mainly transition between the 4F to 4F transition or 5D to 4F transition. These are belongs to the lanthanide ions electronic configuration. The outermost orbital configuration should be in the 4F or 5D to 4F transition. So that is the mainly belongs to the lanthanide ions. That is the first. Next, the visible luminescence of trivalent dysprosium 3+ ions. See in lanthanide ions there is 14 elements are there. In among the 14 elements, today we are going to discuss about the dysprosium 3+ ions. That is one of the lanthanide ions, dysprosium. That is a trivalent dysprosium. Mainly consists of the narrow lines in the blue region. That is the blue region. You can see dysprosium 3+ ions exhibit the blue emission and also yellow emission. The blue emission from starting from 470 nanometer to 500 nanometer. That emission wavelength belongs to the transition of quarter-F 9/2 to 6H 15/2, the excited state to ground state. Ground state of dysprosium 3+ ions is 6H 15/2 transition. So these are the comes from the blue region and also yellow region from 570 nanometer to 600 nanometer. This transition belongs to the quarter-F, the excited state level. Quarter-F 9/2 to ground state 6H 13/2 level. So these are the important emission transition in the visible luminescence of the trivalent dysprosium ion is mainly blue emission as well as yellow emission. These are the strong emissions in the dysprosium 3+ ions. So the later one belongs to the hypersensitive transition, mainly belongs to L equal to and J equal to, which is strongly influenced by the environment. Environment is nothing but the surrounding ligands is mainly change the environment of the dysprosium 3+ ions. Whenever this interaction with oxygen ions, Dy2O3. So at that time it will be interaction that is change the strongly influenced by the environment. So among the oxyfluoride glasses, the fluorophosphate glass. So present study we are used is fluorophosphate. This is one of the important glass property. The fluorophosphate have been of the great interest because of its high optical quality. It possesses the high optical quality, low melting temperature, and relatively high density and good chemical durability. It is desirable that the laser glass has a large emission cross section, long fluorescence lifetime, and a narrow emission bandwidth. These are we are going to get this in this dysprosium 3+ doped glasses. We are getting the important properties. This is one is highly optical quality, low melting temperature, relatively high density, and good chemical durability. And also it is useful for the desired laser glass applications we can use for the different kind of applications, because it's having the large emission cross section, at the same time long fluorescence, that is longer lifetime, and also narrow emission bandwidth. These are the important parameter to study the laser transition, that is laser properties. That is the emission cross section should be more, at the same time lifetime should be more, at the same time narrow emission bandwidth. These are comes to the important to application for the laser applications. So disposing three-phase doped glasses mainly used for white light emission applications. We are using for the dysprosium three-phase doped lead fluorophosphate glasses. Next, coming to the in host glasses, what kind of modifiers we use in the dysprosium three-phase doped fluorophosphate glasses? First, K2O, potassium oxide. See, potassium oxide is the best modifier to achieve good properties. Also, K2O is often used to modify for low field strength cations, where K plus improves the mechanical properties which are precursors to good laser glass. So this is a mechanical property. It will improve the good mechanical properties whenever you are using the modifier as a potassium oxide. So this is one of the good laser glass applications we can use for the potassium oxide, one of the best modifier in our host material. That means fluorophosphate glasses, we are using one of the modifier as K2O, that means potassium oxide. So it can improve the mechanical properties such a way, more value of the mechanical properties. Second modifier is aluminum oxide. See, aluminum oxide is often used to modify the glass structure, which improves the chemical stability and physical properties. So whenever using potassium oxide, it will improve the mechanical properties, the mechanical strength of the laser glass. And if you, whenever you are adding the aluminum oxide Al2O3, it will use the improve the chemical stability as well as physical properties. The aluminum 3 plus ions not only affect the thermomechanical properties but also laser properties. So this also useful for the laser properties. So after that, the addition of metal oxides such as sodium oxide, so it reduces the viscosity of the melt towards lowering the melting temperature. Whenever adding the sodium oxide, generally fluorophosphate glass melting temperature will be 1200 degrees centigrade. Whenever adding the sodium dioxide, it will reduce the melting temperature from 1200 degrees centigrade to 1000 degrees centigrade. So that is purpose we are using for the metal oxides, that is sodium dioxide. It reduce the viscosity of the melt towards the lowering the melting temperature, and also control the tendency towards the crystallization, and also it control the tendency towards the crystallization property. So these are the important property of the sodium dioxide. Next, in the presence of lead fluoride. So finally in this host glasses we are using lead fluoride. So PBF to improve the emission cross section of the fluorophosphate glasses. Moreover, the addition of lead fluoride decrease the host phonon energy. This is very one of the unique property in the phonon energy. Phonon energy means vibrational energy. Phonon is nothing but a vibrational energy. Whenever adding the lead fluoride content, it will decrease the host phonon energy, thereby suppress the non-reactive losses. Whenever this suppress the non-reactive losses, it will improve the emission cross section value. Emission cross section should be increasing. Whenever the low phonon energy, it will give the quantum efficiency also more compared to other fluorophosphate glasses. That is why we are using here lead fluoride content. Whenever fluoride content adding to the phosphate glasses, it automatically it decrease the host phonon energy. That is why it will improve the quantum efficiency and emission cross section value will be increasing. These are the one of the important laser property for the laser glass spectroscopy. So in this present study, we are using the white light emission in dysprosium three-phase doped lead fluorophosphate glasses. These are the introduction of the fluorophosphate. So finally, what are the important parameter we are going to study in this dysprosium three-phase doped lead fluorophosphate glasses? First, the dysprosium 3 plus ion corresponds to the quarter F 9/2 6H 15/2 magnetic dipole transition. This is one of the important transition of the dysprosium 3 plus ions, that is in the region of blue region, that is 485 nanometer, and quarter F 9/2 to 6H 13/2 electric dipole transition. This is comes in the yellow region, that wavelength is 576 nanometer, necessarily for full primary color displays. Whenever we are blue yellow Y by ratio, Y means yellow, Y by B, that means Y by B ratio means yellow color and blue ratio. So whenever this ratio will be tuning, we can get the white light emission. So that is why we are using Y by ratio is very important in the white light emission. So yellow color and blue color, we have both these colors we are tuning, we can get the white light emission. So that is why this is one of the important application for the white light emission in the dysprosium 3+ doped lead fluorophosphate glasses. So fluorophosphate glasses, both fluoride and phosphate glasses, this important property first is low for energy. Whenever adding the lead fluoride, that means in phosphate glasses we are adding the fluoride content, lead fluoride. At that time automatically it will reduce the low phonon energy. And second is good moisture resistance and physical and chemical durability. Whenever adding the aluminum oxide and potassium oxide, automatically it will improve the physical and chemical stability values and mechanical properties values. Next, last is low nonlinear refractiveness also, it will improve the. And finally, high transparency from the near UV ultraviolet region to infrared mid-infrared region spectral range. We can scan the highly transparency in the dysprosium 3+ doped lead fluorophosphate glasses. These are the important parameter in the case of dysprosium 3+ doped lead fluorophosphate glasses. Next, coming to the material selection. How we are choosing the material selection. In the present material section highlights the fact advantages behind the selection of fluorophosphate glass systems for the present study. In this present study, we are focused or concentrated on the white light emission in dysprosium 3+ doped lead fluorophosphate glasses. This chemical composition of the dysprosium 3+ doped lead fluorophosphate glasses is 43 mole percent of P2O5, that means phosphate, is 16 mole percent of potassium oxide, 9 mole percent of aluminum oxide, and a 24 minus X of lead fluoride content, and 8 mole percent of sodium dioxide Na2O, and X mole percentage of dysprosium oxide. So these are the dopant. So we are impurity of the post glasses, we are doping here dysprosium oxide Dy2O3. This is the lanthanide ions or rare earth ions. So after that, year after, we are referred as if 1 mole, that means first we are different X's, different concentrations of, in the case of mole percentage, from starting from low concentration 0.01 mole to 2 mole percentage. So first we can refer as either lead fluoride dysprosium 0.01, that means low concentration. Next one is 0.05, that is PbFb Dy005. Next, lead fluoride phosphate, that means 0.1 concentration. Next, 0.5 concentration, and 1 mole and 2 mole. Here in this paper we are referred as like this, that is lead fluorophosphate doped with dysprosium 3+ ions. Concentration starts from 0.01 mole percentage to 2 mole percentage of dysprosium oxide. So these are the chemical composition of the present study lead fluorophosphate glasses. So next is the experimental technique or preparation of the dysprosium 3+ doped lead fluorophosphate glasses. This we are using. The preparation technique is well-known technique, that is the melt quenching technique. By using the melt quenching technique, we are going to fabricate and synthesize the dysprosium 3+ doped lead fluorophosphate. So previously we mentioned compositions. So in here we required compositions. Chemical compositions are phosphate P2O5, potassium oxide K2O, and aluminum oxide Al2O3, and lead fluoride PbF2, and sodium dioxide Na2O, and dopant of dysprosium Dy2O3 concentrations. So in this, that chemicals we are used to weighing the first. Initially we have to weigh the batch composition. We can take from weight percentage, that means 8 gram to 25 grams of chemical composition. After weighing the chemical composition, we are keep that chemical in the platinum crucible and for the melting purpose. So here melting temperature of the dysprosium 3+ doped lead fluorophosphate glass is 1060 degrees centigrade. Time duration is 60 minutes, means 1 hour we have to keep at the temperature of 1060 degrees centigrade for the melting. After melting, you have to pour into the preheated brass mold. Here we have to pour the, after melting the chemicals, we have to pour into the preheated brass mold at the temperature of 350 degrees centigrade for 15 hours we have to keep. So this handling is below the glass transition temperature. That is, in the case of lead fluorophosphate gases, glass transition temperature is 380 degree centigrade. So we have to below the 380 degree centigrade. That means we are taking as a 350 degree centigrade. We are keeping the annealing at the temperature of 350 degrees centigrade for 15 hours. So after cool down to the room temperature, we have taken to the furnace from the this glass materials. We have to cut the pieces and the small pieces and send for the polishing. After we have to characterize the different kind of optical and luminescence properties. Initially, we have to measure the excited profile because this excited profile shows the prepared glass sample shows the glassy nature or crystal nature. Whether we have to confirm by characterizing by using the excited profile, we have to confirm the glassy nature. So by using the excited profile, we can get the broad bands of the glassy peaks. This is shows the this prepared glass sample shows the glassy nature. So we are confirming the glassy nature. Then after we can send for the different kind of optical and luminescence measurements. So these are the experimental technique or methods for characterization. First, we measure here Raman analysis, and second one is optical absorption spectra. Next one is fluorescence measurements. So initially Raman analysis. So Raman spectrum is obtained in backscattering geometry lab RAM HR800 spectrometer used to measure the Raman analysis. Here using the excitation sources 540 nanometer of argon ion laser, that means AR plus laser and excitation source. So by using the argon laser, we are measure the Raman spectrum analysis. The second one is absorption spectrum. Here Perkin NMR spectrometer lambda 650 nanometer wavelength range from 250 to 2500 nanometer. We are studying by using the optical absorption spectra by using the lambda 950 spectrophotometer. Next, fluorescence and lifetime measurements we are measuring here. The fluorescence and lifetime measurements were carried out by using the Joubin-Wayan fluorolog3 spectrophotometer using xenon arc lamp as a radiation. So the excited source is the xenon arc lamp. By exciting the samples of dysprosium 3 plus ions, we are using the excitation wavelength is 386 nanometer. So from all the measurements we are carried out at the room temperature only. So we are measuring the Raman analysis and optical absorption and luminescence and lifetime measurements. All measurements we are carried out at room temperature only. Next, there is some discussion. First, we are measuring the Raman spectrum. So Raman analysis. So Raman analysis, we are measuring the wave number versus Raman intensity. We are getting the different kind of Raman energy peaks, that is 340 centimeter inverse, 527, 624 and 748, 910 centimeter inverse and 1066 centimeter inverse and 1108 centimeter. This is in this Raman analysis, which peak we are getting the maximum intensity of the Raman spectrum. That intensity peak shows the phonon energy band. That is the different kind of bands we are observing, but different intensities, low intensity and high intensity. In this Raman analysis, which band we are getting the maximum intensity? So comparing all the Raman bands, we are getting the 1108 centimeter inverse band is the intense band. So in this lead fluorophosphate glasses, we are getting this emission shows the phonon band, phonon energy. So it is known that the phonon energy of the host can be defined as highest vibration energy of the host, which can be measured from the Raman spectrum. From figure shows it is found that the maximum phonon, the maximum intensity band is observed at 1108 centimeters. That is studied glass, which plays a major role on the optical property of the luminescent ions. That means dysprosium 3 plus ions. In this lead fluorophosphate glasses, we are getting the phonon energy is 1108 centimeter inverse. This is the phonon energy of the present studied glass sample. Next, coming to the optical absorption spectra. So optical absorption spectra of lead fluorophosphate glasses of 1 mole concentration. This is the 1 mole concentration of dysprosium 3 plus doped lead fluorophosphate glasses. This is the A UV visible region, B is the near infrared region. So we are getting the from ground state 6H 15 by 2. This is the ground state of dysprosium 3 plus ions to the different kind of excitation energy bands. This is absorption bands from different excitation states from ground state to different excitation states. So here getting the 1, 2, 3, 4, 5, 6, 7 bands in the UV region and 1, 2, 3, 4, 5, 6 bands in the near infrared region. So these are the optical absorption bands from the ground state 6H 15 by 2 different excitation state of the dysprosium 3 plus doped lead fluorophosphate glasses. By using the absorption bands, we are studying the JO parameter means judo of rate intensity parameter. That is, JO means judo of rate intensity parameters. This is the intensity parameters of the dysprosium 3 plus doped lead fluorophosphate glasses. In this, we are comparing the present glasses lead fluorophosphate glass of 1 mole concentration of the dysprosium 3 plus ions. We are getting the JO parameters is omega 2, omega 4, omega 6. These are the three important parameters of the JO parameters. So in our present study, we are getting the omega 2 value by using the JO intensity parameter equations. We are calculating the, by using the reference 7 and 8, we are calculating the JO intensity parameters. In that calculations, we are getting the omega 2 value is 7.12, omega 4 is 1.59, and omega 6 is 2.20. That means trend is omega 2 is more, and omega 6 and omega 4. These are the JO parameter trends follow the omega 2 is more, and next omega 6 and omega 4. So that values we are comparing different host classes. So this is different host classes and different fluorosilicate and fluorogerminate, barium fluoroborate, and different kind of host classes we are comparing our present studies in with different other glass host of the dysprosium 3 plus dope glass systems. So in this case, we are getting the omega 2 values more. That means compared to omega 4 and omega 6, this we are getting omega 2. This means covalency will be more compared to omega 4 and omega 6 in the present class shows the 7.12 of the omega 2 value. That shows the it's having the dy to dy is a dysprosium to dysprosium interaction. Covalent bond is more compared to other host classes. That is shows the omega 2 parameters. Next, coming to the in resonant discussion, we are studying the excitation and emission spectra. So in first figure shows the excitation spectra of the dysprosium 3 plus doped lead fluorophosphate glasses. In this, we are using the 576 and emissions are 480 nanometers, 485 and 576. So solid line shows the 485 nanometer of excitation for emission, and other one is 576 nanometer dotted line. These are the different emissions. We are measuring the excitation spectrum. Next, this figure shows the normalized emission spectra of different dysprosium 3 plus dope lead fluorophosphate glasses. Here, different concentration from starting from 0.01 mole percentage to higher concentration 2 mole percentage. Here, see the this is blue band, this is yellow band. So 450 to 500 nanometer in between, we are getting the blue transition. That is a quarter-F 9/2 to 6H excited state. Quarter-F 9/2, 6H3 excited state to ground state. This is excited to ground state. So excitation with 386 nanometer. We are excited emission spectra. We are exciting with 386 nanometer. We are getting the two emission bands. One is blue region, other one is yellow region, and last one is small energy. That is a red region. That is a less intensity. So that is a 6F 9/2. Quarter-F 9/2 to 6H 11/2. These are the different transitions of the dysprosium 3 plus dope lead fluorophosphate glass of the emission spectra. So from excitation and emission, what kind of data we are observing? From the excitation spectra of lead fluorophosphate glass monitoring the emission bands at 485 and 576 nanometer, the transition of the excitation spectra are assigned starting from 6H15/2. That is the ground state. Based on the free ion energy level, we are study the possible transitions of the bands are the 6H15/2, quarter-F 5/2, and 6B3/2 transition from the excitation spectra, which are not amenable from the covalence in absorption. So these bands we are not observing the absorption spectra, but we are observing in the excitation spectra. That is mainly due to the free ion energy level structure of the dysprosium 3 plus dope lead fluorophosphate glasses. From the luminescence spectra or emission spectra, we are recorded the function of dysprosium ion concentration. Two strong emission bands we are observed. One is blue emission at the wavelength of 485 nanometer. Other one is yellow emission at 576 nanometer. Corresponds to the quarter-F 9/2, 6H15/2, and quarter-F 9/2, 6H13/2 transitions. And a weak band, that means red emission also we have observed, that is weak transition, and emission band at red emission 666 nanometer corresponds to quarter-F 9/2, 6H11 by 2 transitions have been observed under the excitation of 386 nanometer of the excitation wavelength. The intensity of peaks increases with increase of concentration. See here, the increase in the concentration, the peaks intensity will be the quenching of intensity. That means concentration disposable ions is up to 1 mole per second and then decrease. Starting the increasing concentration, it will be increases and suddenly it will decrease. The decreasing shows the quenching of intensities increase which disposition 3 plus ions is due to the increase of non-radiative energy transfer through cross relaxation channels. This is a, whenever increase the concentration up to 1 mole percentage, it will be increasing with increasing concentration. After that, it will be decreases. That is a quenching is started. That means a higher concentration, that is 1 mole concentration, this luminescence intensity will be decreasing. That is a mainly due to the non-radiative energy transfer through the cross relaxation channels. So that is we are going to discuss in the next slides. So from emission spectra, we are calculating the different parameters. This is important parameter for the laser applications. First is the lambda peak, that means wavelength of the peak wavelength emission. Next, radiative transition probability AR. Next, branching ratio PR value and delta effective value and stimulated emission cross section values. So these parameters is very important parameters to do the laser applications. So in this lambda p, this we are getting in the emission transition in the dysprosium 3 plus doped lead fluorophosphate. We are observing the 3 laser transitions. One is 485 nanometer, other one is 576, and the other one weak transition is 666 nanometer. In this, among these two transitions, these two are the strong transitions, blue and yellow transition compared to red transition. So that stimulated emission cross section values 0.30 and 2.63 and 0.48. Among three transitions, this yellow transition value will be more compared to blue and red. So by using the Y by ratio, yellow and blue intensity ratio, we are calculating the white light luminescence also in the case of dysprosium 3 plus dope lead fluorophosphate glasses. So this delta effective value, stimulated cross section value, we are calculating it by using this formula. This is a lambda p, that means peak intensity, and 8 pi cn square delta effective wavelength. Next, transition probability AR value. By using these values, we are calculating the stimulated emission cross section of the dysprosium 3 plus dope lead fluorophosphate glasses. Delta mu is the full width of magazine. Beta R is the branching ratio of the each and every emission peak. Next, white light emission. This figure shows the CIE 1931 chromacity diagram. 1931 chromacity diagram. By using this chromacity diagram, we can evaluate the white light emission or white light emission analysis. So by using this color coordinates, we can calculate the dysprosium 3 plus dope glass. So in this color coordinate diagram, we are getting the white peak. This is the white light emission. This is blue, green, red. So this part shows the white light. So in this, whenever you are getting the XY color coordinates value, should be fallen to in this region that shows the white light emission. So in here XE, YE, that is the equivalent white color coordinates value is 0.33, 0.33 X and Y value. In the sample, in our present glass sample value, we are getting X and Y values 0.31 and 0.34, and XD and YD values 0.03 and 0.43. These are the value intersection of this white light region. So here this indicates that the 1 mole percent and 2 mole percent of the lead fluorophosphate gas is bit higher color purity and emits a bright white light, which are useful for the development of white laser emitting device. White LED device applications we can use for the dysprosium 3 plus dope lead fluorophosphate gas. By using this formula color purity, so square root of xs xy whole square plus ys minus yi whole square by square root of xd minus xy whole square plus yd minus y whole square into 100%. By using this formula, we can calculate the color purity, that means white light purity, how much is there. In the case of 1 mole percentage, we are observing white light is 0%, and whereas the 1 mole percent is 7%, and for the 2 mole percent is 7%, around 7% of the white light we are getting the dysprosium 3 plus dope fluorophosphate glasses. So by using the chromacity diagram, we can calculate the color purity and at the same time color coordinates also we can calculate. By using the color coordinates only, we can calculate the color purity also. Next, coming to the decay time, lifetime measurements of the dysprosium 3+ dope lead fluorophosphate glasses. See the here different here lifetime versus normalized intensity. Here low concentration of 0.01 to higher concentration 2 mole percentage. We are taking the excitation wavelength is 386 nanometer and the emission blue emission 485 nanometer. We are monitoring the decay time measurements. Here low concentration 0.01 mole percent shows the single, that is single exponential nature, that means no energy transfer. It shows the single exponential nature of the low concentration of the disposing 3%. If you increase the concentration of high concentration more than equal to or greater than equal to 0.5 mole percent of disposing ion, it exhibits the non-exponential nature. That means so single exponential means at low concentration only it will exhibit the single exponential. Whenever the increase in the disposable ion concentration, it is single exponential is converted into the non-exponential nature. That is mainly due to the cross relaxation channel using dipole-dipole transition. That is the lifetime we are calculating the from using this format tau exponential lifetime by using the integral of t into I of t intensity and divided by integral of I of t dt. So by using this formula, we can calculate in the exponential lifetime of the dysprosium 3+ ions. But after non-exponential nature, this is higher concentrations we are fitted with Inocuity Hirayama model, that is IH fit. That is IH model, Inocuity Hirayama model at S equals 6 shows the dipole-dipole nature. The non-exponential nature is mainly belongs to the energy transfer through cross-selection channel. That also it by using the IH fit, we can confirm the its nature of the dipole-dipole type nature while fitting the decay time measurements. So these are this data we are going to observe in the lifetime measurements. Next, finally, this is the partial energy level diagram of the dysprosium 3+ ions lead fluorophosphate glasses. So these are the dysprosium 3+ energy level diagram from dysprosium 3+ from ground state 6H 15/2 different excited states. So we are pumping the 386 nanometers. After excited state, it will be non-radiative and comes the emission transitions. So blue emission at 485 nanometer and 576 yellow emission and 660 weak emission is 660 nanometers. So we are getting two strong emissions and one weak emission. So we are using the Y by ratio only. We are calculating the white light emission. These are the resonant energy transfer channels. This is energy transfer through cross relaxation channel. That means from here to here, this quarter F 9/2, quarter F 11/2 plus 6H 9/2. This energy transition is equal to the quarter F 11/2 6F image. So whenever the same energy will be matches, so it takes place energy transfer from higher energy to lower energy. So that is the energy transfer through cross relaxation. Whenever the energy bands is same, equal, here resonant energy transfer, that means quarter F 9/2, 6H 15/d energy, this from this energy to this energy is same, quarter F 9/2, 6H 15/2. So this is the resonant energy transfer, means same energy bands will be matched. But here, whenever the higher energy to ground energy and higher energy to ground energy, whenever this energy and this energy same, equal means at that time energy transfer will takes place from higher energy to lower energy. So by using this energy channel only, we can whether it is a dipole-dipole nature and energy transfer through cross relaxation channels. By using the energy level diagram only, we can study the energy transfer through cross relaxation channels. Also, we can study by using the partial energy level diagram. Next, finally, conclusion or summary of the white light emission in dysprosium 3+ dope lead fluorophosphate glasses. The higher magnitude of omega 2 in our present class, we are getting the 7.2 value of the omega 2 value. In the study class suggests that the higher degree of covalence, we are having this shows the higher degree of covalence in dysprosium to oxygen bonds and higher asymmetry around the dysprosium 3+ ions. That is the intensity parameter, JO parameters shows we are in this omega 2, omega 4, omega 6. Now among the three intensity parameters, we are getting the omega 2 parameter value is high, that shows the covalency of dysprosium to oxygen bond and higher asymmetry around the dysprosium 3+ ions. That is shows from using the JO intensity parameters. Next, in emissions parameter, the higher value of branching ratio and stimuli emission cross section of the quarter of 9 by 2 6 meter transit suggests these glasses can be used as potential laser cross transition. So for laser applications, we are using this transit because we have the strong emission band at quarter of 9 by 2 6H 13 by 2. That is why this is used for the yellow laser applications. Also, we can use for the disposal filterscope fluorophosphate glasses. This lifetime measurements the non-exponential decay rates found the higher disposal filters in concentration and our non-exponential nature is well fitted with the IH model. That is Inokiti Iriyama model for S equal 6 shows the dipole type of the energy transfer mechanism. Next, last is the an intense white light emission has been observed and found to increase the disposable ion. Whenever increase in the disposable ion concentration, the white light emission will be increases. These are the summarized conclusion of the white light emission in disposable filterscope lead fluorophosphate glasses. So these are the references are cited in the present talk. So these are the different references. In this present work is mainly focused in this reference. This is myself, Keshavan, my supervisor is Professor Jaishankar. We are publishing this work in the Material Chemistry Physics in 2011. This is one of the highly cited paper in the present study, that is white light emission in disposable filterscope and lead fluorophosphate glasses. These are the first we have observed the white light emission by tuning the yellow emission and blue emission. We are tuning the Y by ratio. We can get the white light emission also in lead fluorophosphate glasses. These are the important references in the present study. Next class we are continuing with the next session. Thank you once again. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.